This is the Drone Project. I'm Tan.
I'm Steven.
And I'm Sean.
How long do bridges last? Countless cars drive over bridges. The accumulated stress from these vehicles build up over time and cause damage. Large operations are needed to ensure that these bridges are safe to operate, which often result in lane closures and consumes tons of resources. Is there a better way? We propose using a drone equipped with sensors to detect the faults in bridges. The drone will remove the need for lane closures and will be more cost efficient. Benefits of a drone. Drones possess the ability to fly and are relatively small, allowing them to get to hard-to-reach places on the bridge. Drones are not limited to only inspecting bridges, however. They can have practical applications in assessing damages in other forms of infrastructure, such as windmills or highways. Our vision. We plan to create a drone with autonomous capability to survey bridges and detect any faults within structures. Our drone. Our customized drone carries various sensors and cameras. We utilize Fusion 360 to design the drone's body. We will then print the designs out in our 3D printing workshop. I will now pass it on to Tane to discuss about the designing of the drone in CAD.
Thank you, Steven. For our first prototype of the arm, the design was much too bulky and it weighed way too much. For our next iteration, we removed material in strategic areas to reduce weight but not compromise on structural integrity. We ran multiple stress simulations before printing out the arms to test the qualifications of the design. As you can see here, the arm spreads out the load without breaking. To determine the force acting on the arms for our simulations, we used a force meter to test the thrust generated by our motors. In the simulation, we increased the force for a proper safety margin, and according to the simulation, the arm handles it without danger of breaking. We used a water jet cutter to fabricate our aluminum centerpiece that holds the drone body together. Our first flying prototype, seen here, has exposed wires and electronics, which is not ideal. To fix this, we designed panels that cover the wires and use pre-existing mounting holes to save weight and complexity. The flight computer, or main flying computer, is also protected in the event of a crash. To make replacing the battery user-friendly, we added a battery holder that separates the wires from our power source. Our motor controllers fit in the arm so they can be air-cooled. The landing gear are printed with a hollow infill to make them sturdy but light, allowing them to be long enough for us to mount the sensor array underneath. These legs have a wide stance to keep the drone balanced during takeoff and landing. Now here's Steven to talk about the optical flow sensor.
Thank you, Tane. Our drone utilizes an optical flow sensor to hold its position instead of GPS. The way the optical flow sensor works is by taking multiple pictures of the ground and compare them to one another to determine the change of position. The same technology is used on the Ingenuity helicopter on Mars. Mounting the flow sensor. Our optical flow sensor cannot be mounted on the drone's center of rotation, so the offsets need to be accounted for in the code. Here, the values in this table indicate the sensor's relative position in the X, Y, and Z plane. Now, to show how the optical flow sensor works. Here, we have our drone in action. As you can see, it's holding its position pretty well. It's not falling to the ground, nor is it going up to a roof. And it's not drifting too much. It has slight drift, but obviously it's correct in its positioning.
So I'll be introducing the LiDAR module. So the way the LiDAR module works is it takes a time-of-flight sensor, which is the LiDAR, and it shoots a laser beam out, and then it measures how long it takes for that laser beam to return to the sensor. So then we take that data along with the position that the servo is in that is rotating the LiDAR, and then we plug it into the Pythagorean theorem to plot a set of points, which you can see with this graph here. And then this process repeats several thousand times to create an actual 3D model, which it will then plot along with the GPS data. So now, in order to actually test the LiDAR, we created these testing blocks, which have a series of cracks, which we can aim the LiDAR at, and when we run it, we can see how well it picks up these cracks. So we 3D printed these, and they really help to improve our data set. So not only do we use a LiDAR system, we also use a stereo camera. So the way the stereo camera works is it takes two images, which is similar to how your eyes work, and then it looks at the differences between the two images. So in order to actually view the data from our stereo camera, we attached it right above the LiDAR, which you can see in this bottom photo. And then it connects through our Pi. So both of them are streaming through the Pi to collect all the data.
We are coding the Raspberry Pi using VS Code and SSH. SSH stands for Secure Shell, and it lets us remotely access the Raspberry Pi using our laptop without having to hook up a monitor and keyboard to the Raspberry Pi. We can run commands through SSH and also save files onto the Raspberry Pi. And this is how we're doing all of our coding. For coding the camera, you can see the graph here, how the image is captured. It is turned into an array. It is then turned into a byte stream, which is sent using TCP over the internet. The byte stream is then received, deserialized, and then saved and displayed. TCP connection is a reliable, ordered, and error-checked communication channel between two devices over a network. It is often called a three-way handshake. And what happens is the client initiates the connection, then the server acknowledges it, and then the client again requests a file, and then the data is sent. This allows for secure data transfer. So here we have part of the code for the stereo camera. This part of the code is on the Raspberry Pi. And what we have here is this sets up the socket for the serial port. So this just sets it up, and then right here we just wait for a connection from the other code. So our stereo camera is plugged into the Pi's USB port, and then this just captured the data from that port. And then right here we just have a loop, and what we can do is serialize every single frame, and this loop just sends it continually, keeps updating and sending it to the other code. Now over here, this is on our laptop, and this code, it first of all has to connect to the Raspberry Pi, and that's what it does here. And you see we have the IP address for the Raspberry Pi, so it knows where to connect. And the rest of this code is about receiving the data and then deserializing it. So all of this deserializes the code, and then this prints it out on our live stream. So all we have to do is run this code, and you can see that we're waiting for a connection. Now on the other end, we can just run this code, and now we have the live stream up and running.
Right now you are viewing onboard footage from the stereo camera. The stereo camera is connected to the Raspberry Pi through USB. The Raspberry Pi sends the information to the computer wirelessly. We can use this information to visually identify cracks in bridges.
So here we have the code that is controlling the LiDAR. The first really big important thing is this right here and this right here, these two lines. So what that does is that creates a multi-process. So the reason that we do that is because we are controlling both of our servos and our LiDARs manually, and each one of those runs at a different rate. In order to be able to actually sync those up together, we have to run those on a completely different thread than the main one. So what these lines do, again, is they create the processes and actually start that multi-threading. Now what we do here is we are pulling in the data from the LiDAR, and we are just adding it to the end of a list. And then whenever we get data from a servo, we are going to take all the LiDAR data, average it, and then we are going to take that average distance along with the servo here, and then we're going to plug it in to pull out the x and the y coordinates using trigonometric functions. So if we look at what the servo is doing, the way that it works is when we call the multi-threading, it calls this method here, which will send commands to move the servo through the library that we wrote. And it'll alternate between 48 and negative 39 for the positions of the x. However, at the end of it, it will skip, which is why you can see the reverse will strip. It will skip the last few digits to deal with extra slack mechanically in the system onto the LiDAR. So the way this works is this communicates over serial with the LiDAR, looks at the bus, and then it takes in all the data, and then it breaks it apart by each byte. And then from that, it pulls each individual distance from that.
Here you can see the LiDAR moving left and right. And as it scans, it is continually collecting data.
The entire drone project roughly costs $4,000, making it very competitive in pricing when compared to other commercial alternatives. Further implementation of this technology and mass production of the product will only aid in driving costs down.